Hi and welcome back. This is Lesson 2B. Lesson 2B, we're going to be doing the second part of this third learning outcome, or I suppose the third learning outcome here, which is a derivation of the equations of motion, v equals u plus at and f equals ut plus a half at squared using calculus methods. So this is probably one of the hardest mathematical lessons. It's definitely going to use up a lot of your higher mathematical knowledge. We're going to do a wee bit of integration here, but hopefully you can follow this through. If you can get through this, this is about one of the trickiest bits of math that we've got here. Having said that, it's not too bad, and it's a wee bit like higher physics in the sense that it's very mathematical at the beginning, and then it gets a bit easier afterwards. You might notice I've also actually circled down here some of the equations, because the good news is that some of the bits down here we will already have covered by the time we get to them. Okay, so starting off, what you have to do here is you have to start off with the relationships that we've got up to now. So up to now we've had that v equals ds by dt. We have had that the acceleration equals dv by dt, or to put it another way, it equals d2s by dt squared. Right, assuming you're okay with them, then our next task is going to be to use these equations here and do a wee bit of integration. Now, normally in physics we are not quite as particular as maths as far as mathematical notation goes, but here is the exception. I'm afraid, unfortunately, you do have to pretty much learn these off line by line. If you miss out any little bits, even though you or I might not think it's ridiculously important, it's marked in normal physics way, which means that you will immediately start losing marks, or in fact will stop marking. So it's very, very important. These do come up quite a bit. When they come up, there's something you can learn off, but hopefully you understand it first of all. My advice in all these things, and certainly advanced higher physics, you really must try to understand before you just learn up. Okay, so what we're going to do is we're going to integrate. We're going to start off with a equals d2s by dt squared. Now, it's not the easiest one to start with, and I do understand that, but one of the reasons I'm starting with it is for that reason. What we're going to do is we're going to integrate that with respect to time. Now remember, integration is effectively the backwards version of differentiation. So quite often I think of it as going s, v, a, like that. This is effectively differentiation. And then going back the way, from a to v to s, this is like integration. Oh, integration. So really what we're doing is we're going to be going from s to ds by dt to d2s by dt squared. Going in that direction is differentiation, and going in this direction is integration. So that's effectively differentiation, that's integration. So when we integrate this, what we're going to do is we're going to start off by writing out the equation as we've got there. So I'll actually write it out a little bit bigger so it's easier to see. So a equals d2s by dt squared. After that, what we're going to do is we're going to integrate both sides with respect to t. So we'll do integration mark a with respect to t, and on this side we'll do integration mark d2s by dt squared with respect to t. So we're doing the same thing to both sides. It's effectively an integral equation. Now if we integrate this, we're going to get a times t plus a constant. We don't know what the constant is, but that doesn't really matter too much at this stage. And then on this side, if we integrate that, if we integrate this with respect to t, we're effectively going back the way. We're going from this to this back the way. And so what we actually do, I sometimes think of it as almost multiplying up onto the top row and kind of cancelling out the squares, but it doesn't really work like that. That's not real maths, but that's the way I think of it when I forget. So this ends up being ds by dt. Remember, we really only need, we wouldn't actually need a constant anyway on this side, but we really only need a constant in one place, because if there were two constants, that whenever we're integrating the two constants on either side, well then they just combine to make one constant. So what we've got is we've got ds by dt equals at plus k. Right, now remember that ds by dt is actually your speed as well. So this bit here is really your speed. Now this isn't, the stuff in red here isn't needed as part of the integration, but it's just to explain it. So this is really saying that the speed is at plus a constant. Well, at the very beginning, when, this is what you do in maths, you do it with limits. So when time is 0, so at the very beginning of this, what is the speed going to be? Well, the speed is going to be our initial speed, which we're going to call u. At the beginning, when time is 0, then the speed is the initial speed, u. So what we actually say is that when time equals 0, ds by dt is equal to u. So that basically means that our constant is actually going to be u as well. Okay? Our constant, oh, should make that, that's not one word, it's not sock. So our constant is u. Now to explain how that works, and this is again something you don't need to do, but when time is 0, at plus a constant equals ds by dt. So when time is 0, then that's a times 0, which is going to be 0, plus a constant equals the initial speed, which is u. Now because this ends up being 0 here, we end up with basically 0 plus k equals u, and so the constant has to be u. I'm doing this quite quickly. You will have to probably go through this quite a few times yourself, and actually I'd advise writing it out several times to get it into your head. But understand it first of all, step by step, and then go on from there. At the time of t, at any other time, so at any other time, which could be later on, then our final speed, or our speed at that time, is going to be v. Now I will give you a set of notes that has this in it as well, but it's worth actually looking at there. So basically, if we've got this equation at the top here, so I'm going to put this equation down here. So ds by dt equals at plus a constant. But remember, the constant is going to be u, right? And remember that this ds by dt is going to be whatever the speed is at a given time. So we're looking at the time at the speed at 12 seconds, and we'd have our time here would be 12 seconds, and we'd be looking for the final speed. So effectively what we're going to do now is we're going to take this out here, and we're going to put v in instead of that. Now I do sometimes, when I'm doing it myself, I do sometimes shortcut, and I actually do sometimes just actually say the ds by dt is v, and I don't worry too much about this bit here. But it's up to you. I would say putting this bit in is definitely, makes it absolutely definitely correct. And at that point, we've got v equals at plus u, or the way that we normally write it, u plus at. And that's it, proven. There is an alternative method for doing this that I'll show you maybe in an extra little video that I'll upload. Okay, the next one that we need to be looking at is going to be it's going to be taking that equation that we started out, or that we finished up with there, which is basically to say that that v equals ds by dt, or to put it another way, v equals ds by dt, which equals u plus at. So what we're going to do is we're going to take the second part of this, and actually I really should change back to a black pen, because all of this stuff here is actually necessary. But we're going to take the second part of this. So if we start off with v equals u plus at, I'll do what you have to actually write. So v equals u plus at, but we know that v equals ds by dt. So ds by dt equals u plus at. Now what we're going to do is we're going to integrate this on both sides. So the way that we do that, and there's different ways you can do it, you can kind of split something across there, but what I'm going to do is I'm going to kind of integrate it in a very full manner. I'm going to say ds by dt will integrate both sides with respect to t. I'm going to put this into brackets. And this on this side effectively becomes ds. Excuse me. Oh dear. This on this side can be split up. We can split it up, and hopefully you've done this in maths, but you can split it up into u dt plus at dt. Okay? I mean, you can do it straight from there if you want. It doesn't really matter. So the integral of this is actually going to end up being s, and the integral of this left-hand side is going to be ut plus a constant, but we'll leave the constant for the moment, plus, and this ends up being, the t goes to t squared, and then we divide by the index here, so it's a half at squared. But we do have to add the constant in, because we've got a constant of integration here. But remember, at the very beginning, right, if we apply the initial conditions, okay, at the initial time, which is basically t equals 0, the displacement from the starting point has got to be 0, because we're starting off at 0. So, if time is 0, and s is 0, this is going to end up being 0, this is going to end up being 0, this is 0, therefore our constant also has to be, I suppose so you could say, so constant also has to be 0, so it can be taken out, and we're left with s equals ut plus a half at squared, and that's our proof. Now the things that normally cause problems here are, I've seen some amazing, beautifully set out integrations that have missed out dt back here, or have missed out little bits back here, and I have to say I don't think we're particularly maths, therefore I don't think that would necessarily, for me, mean that you should possibly take off all the marks, but unfortunately it is quite harshly marked. You have to make sure you do this. So really what I would like you to do before I give you problems on how to actually apply these is I'd like you to practice these two derivations. These two derivations are ones that you need to know. You really do need to know them off by heart, and so hopefully you can get them and get them right at home. Okay, thank you very much for that.